A heat pump reversing valve is a crucial component in a heat pump system, responsible for controlling the direction of refrigerant flow and thus enabling the heat pump to switch between heating and cooling modes. Reversing valves are often called four-way valves because they have 4 ports or connections for refrigerant flow. The discharge inlet line will always be the single line opposite the 3 other lines. The true suction line will always be a low pressure outlet in the middle of the 3 pipes and directly connected to the accumulator. Depending on the heat pump mode, the 2 outer lines will either be a discharge outlet or a suction inlet. The components of the reversing valve are the valve body, which is the main housing of the reversing valve. It contains various internal components and passages that control the refrigerant flow. Inside the valve body is a sliding mechanism that moves to change the flow of the refrigerant. The slider sits in the support frame, and pistons form a tight seal against the valve body. The valve seat forms a tight seal with a gasket on the bottom of the slider. The solenoid coil is an electromagnetic coil that receives electrical signals from the heat pump control system. The capillary tubes mimic the 4 pipes of the reversing valve. The pilot valve contains various components that respond to the heat pump's mode: the fixed core, the core spring, the core, the stem, which consists of a valve and gasket, and the valve seat. The pilot valve and valve body both direct the flow of refrigerant. The pilot valve's mechanical movement is by electromagnetic force, whereas the movement in the valve body is by refrigerant pressure. Let's take a closer look. First, examine how the refrigerant flows through a reversing valve with a de-energized solenoid coil. In this example, a de-energized solenoid coil represents heating. High temperature superheated vapor from the compressor enters the discharge inlet port, travels into the valve body, and discharges through a side port to the indoor coil. The refrigerant travels through the refrigeration cycle and returns to the reversing valve as a low-pressure superheated vapor. The refrigerant travels towards the valve body and is directed into the true suction port through the slider. From there, it travels to the accumulator. When the system switches between heating and cooling, the thermostat sends a signal to energize the solenoid coil and generates a magnetic field. This magnetic field exerts a force on the core, causing a mechanical motion. The core and stem move, causing the pressures to change in the 2 outer capillary tubes. The high pressure in the capillary tube is now directed to the other side of the valve body, causing a mechanical motion of the slider mechanism and directing hot gas to the outdoor unit. The refrigerant on the other side of the valve body depressurizes and flows back to the pilot assembly through the stem gasket and back to the low pressure suction line. When the thermostat satisfies the cooling call, the contactor at the heat pump de-energizes, but the solenoid stays energized. Without the discharge pressure from the compressor, the valve on the stem opens and equalizes all the pressures in the reversing valve. When the system switches between heating and cooling, the solenoid coil de-energizes. The core spring causes the mechanical motion, resulting in the pressures changing on the outer capillary tubes, pressurizing the other side of the valve body, shifting the slider mechanism, depressurizing the other side of the valve body, and sending high temperature superheated vapor to the indoor unit. In this example, the de-energized solenoid valve results in heating. It's worth noting some manufacturers' reversing valves are de-energized for cooling. Thank you for watching the How It Works video series.